Hello everybody, welcome back. Today we're going to be talking about arc length, part of a section usually with curvature, but this will be part one. This will be just focused on arc length. So let's start by reviewing what we know about arc length for a minute. In prior classes, prior calculus classes, you might have seen this. From A to B, the square root f prime of t squared plus g prime of t squared. And this is how you calculated arc length, probably in Calc 2. All right. Now, for most concepts, so far in our Calc 3 class, we have always just taken what we've already learned and extended it to 3 dimensions. So if we extend it to 3 dimensions, we get L equals the integral from A to B, the square root of f prime of t squared plus g prime of t squared. And then for that third dimension, it's h prime of t squared. All right, and what does this look like? To me, it looks like magnitude. So if r of t is what we're given as a vector valued function, and then we take r prime of t. I'll make a better prime out of that. We get f prime of t plus g prime of t in the j direction and h prime of t k. So if we do the magnitude of r prime, right, we square them, add them, and square root them. So we have the square root of f prime of t squared plus g prime of t squared plus h prime of t squared. And if we look up here at our formula, it looks like we have the very same thing. So we can actually rewrite our arc length formula to be, right, we use S for arc length, from A to B of the magnitude of r prime of t. So this is something very important to keep in mind because, again, we're accessing skills that we've already learned. All right, so let's jump right into a couple of examples and see how we do. So, example 1. Find the arc length of the space curve over the given interval. So I have my r of t equals 2 sine t, 5t, and 2 cosine t. So how do we find this? Well, the first thing we need is we need r prime, right? Because how can we get the magnitude if we don't have r prime? So let's start with r prime. The derivative of 2 sine t is 2 cosine t. The derivative of 5t is 5. The derivative of 2 cosine t is negative 2 sine t. At this point, if you were in my class, showing every step on a derivative wouldn't necessarily be the most essential thing that I'd be looking for. I'd be looking for just enough steps to know that you're not either guessing on the derivative or something to that effect. If you're having trouble with derivatives, I would encourage you to look at one of my past videos on derivatives. All right, so now I need to do my, I can just go right to setting up the integral. So the only way to know this would be I would have to give some additional information in the problem over the given interval. And the given interval is 0 less than or equal to t less than or equal to pi. So that would have to be given in the setup of the problem. So that's the only way to know your limits of integration. Then I'm going to do my square them, square each element, add them, square root them. So I have 4 cosine squared t plus 25 plus 4 sine squared, t. Now I can manipulate this a little bit to bring my cosine squared and sine squared closer together, because I know that cosine squared plus sine squared equals 1. And so I can further simplify this integral before I do the integral. So 4 plus 25, so I have the square root of 29. Now, simplifying this integral just makes it easier when it's time to integrate. So if I integrate, right, I get square root of 29. Oops, excuse me, I don't want to extend that. T, and I'm going between 0 and pi. So then I wind up with square root of 29 pi minus 0. So my final answer would be square root of 29 pi. All right. So again, simplifying before you integrate makes the integral much, much easier. All right. So let's step it up a notch. And let's throw in, all right, so do our next example. I'm going to give my r of t as e to the t cosine t, e to the t sine t, and e to the t. And I'm going to go from 0 less than or equal to t less than or equal to 2 pi. So again, the first thing we need is r prime. All right. Now, the reason I say that we're stepping it up a notch here is we don't just have a power rule. We don't just have a trig function here. I've got an e and I've got a cosine. I've got an e, I've got a sine multiplied together. So we're going to need to do product rule. So why don't you pause the video, execute the product rule on the first two elements. The third element, derivative of e to the t, is just e to the t. And we'll find r, we'll talk about r prime on the back end. All right, I hope you paused the video for just a minute to work out that derivative. I would say not the hardest product rule I've ever had in my life, but if you haven't done product rule for a while, could be challenging. So my derivative I got was e to the t cosine t minus sine t e to the t. I'm going to just shrink that a little bit so I get a little bit more room. Sine t plus cosine t e to the t. And now we need the magnitude of r prime. So let's get in there. Looks like we'll have a little bit of algebra to do. All right, so we got e to the 2t, because if I square my first element, e to the t squared is e to the 2t. Then I've got cosine t minus sine t squared. And then I'm going to add that to, again, same thing, e to the 2t sine t plus cosine t, whole thing squared. Let me just make that a little bit more separate. Plus e to the 2t. All right, so now there's some algebra to do. And I'm going to ask you guys to pause the video to do some of that algebra. If we look over here, right, this over here you need to expand and FOIL. This over here you need to expand and FOIL. But we can also, right, we have an e to the 2t, e to the 2t, e to the 2t in all three of our terms. So can we can actually, before we start doing our algebra, take that out of the square root and just leave it as e to the t. So I'm left with cosine t minus sine t squared plus sine t plus cosine t squared plus 1. Remember, we need that placeholder, because if we ever wanted the e to the t to go back in, we would need a place in the third slot. So again, I'm going to ask you to pause the video to work out the expand and FOILs on those squareds. And we'll pick it up on the back end. So happy hunting. All right, so again, we have e to the t, and then underneath, not only did I expand and FOIL, but I simplified just a little bit. So I wound up with cosine squared t plus sine squared t plus sine squared t plus cosine squared t, and then that plus 1 just comes along for the ride. There were some other terms in there, but they added to 0, so they were eliminated. Now I've got cosine squared plus sine squared, which equals 1. Sine squared plus cosine squared equals 1. So once again, I got e to the t, 1 plus 1 plus 1, which equals radical 3 e to the t. And then I'm going to integrate this from 0 to 2 pi. Now this is a much easier integral, all simplified out, than it would have been if we didn't simplify first. So I definitely recommend that. So for the integral, the square root of 3 is just a coefficient. The integral of e to the t is e to the t. And I'm going between 0 and 2 pi. So I get square root of 3 e to the 2 pi minus, minus square root of 3 e to the 0. Anything to the 0 is 1. So I can just say square root of 3. And I'm okay if you left it like that. If you wanted to factor out the square root of 3 and say e to the 2 pi minus 1, like that, and leave it in factored form, I would have no problem with that either. All right, so let's try something else. All right, so for my last example, All right, remember I told you that arc length, right, was S of t, yes? So sometimes we can take our r of t, our vector, and we can reparameterize our vector to find r of s. Now, the reason we would want to do this is because maybe we're looking for curvature. Now, curvature is the next topic in the section. But sometimes if we have r of s instead of r of t, our curvature could be a little bit easier. So let's do our last example to just talk about reparameterizing for arc length. I'll show you what I mean. And like I said, this is something that could potentially make your life easier down the line, depending on the information you're given in a specific problem or situation. So 1 plus t in the I direction, 1 plus 2t in the j direction, and then plus 3k. That's k. Come on, there we go. All right. So we want to find our vector r in terms of s. And like I said, we would do this in an effort to make our life easier in solving a larger problem. All right, so we'll say that t has to be greater than or equal to 0 because that's a line. So if we were to start by finding r prime of t, just like we did for every other arc length type problem, our derivative would be I plus 2j plus 3k. All right, now I want to know the magnitude of r prime. So everything starts out being exactly the same as before. So I have the square root of 1 plus 4 plus 9, which equals the square root of 14. Now notice, I don't have a specific starting and ending point, just greater than 0. So when I set up my integral, go from 0 to t, square root of 14. I'm going to use u as my placeholder variable. So when I integrate, I get square root of 14u from 0 to t. And when I do the first fundamental theorem of calculus, I get square root of 14t. Now remember, this is our arc length. So s equals the square root of 14t. Now, here's what I'm going to do. I'm going to solve this for t. So I'm going to say t equals s over the square root of 14. And then I'm going to take this and I'm going to plug it into my original vector. Anywhere I see a t, I'm plugging in the s equivalent. So my final answer is going to be r of s. I'll make a better s. Equals, and then I have 1 plus s over square root of 14 I, 1 plus, now it was 2t, so 2s over square root of 14 j. I'm just going to shrink that a little bit so I get a little bit more room. And my last term was 3t, so I'm going to have 3s over square root of 14k. And there is my vector reparameterized for arc length. All right, this was a short one. There is a part 2 for this section. It's going to be focused on curvature. That should be coming out soon. I always endorse getting some extra practice, but I do hope that this short video will be a good support for what you already have or help you get started in finding arc length. Thanks a lot for listening, and I'll talk to you all on the back end. Have a good one.